I would like just go through the program, that's what we are going to do for these 2 days. And after the welcome address, that we'll have a keynote speech by Dr. Fernando Gonzalez. And for each presentation, we have about 20 minutes. After the presentation by Dr. Fernando, that Dr. Maya Donoso will also make a keynote introductory lecture that will take about 20 minutes. After that, we have a photo session that is good. We have also photographers from now, and maybe we find a place for here to have the group photo. And after the group photo, we have tea and coffee break. We have this looks ready now. And after the tea break, that the presentations will continue. That the first presentation session, we have 4 presentations. That each presentation will have 20 minutes, and we try to limit 20 minutes. But in case it's not very much strict, can be some 5 minutes more or 5 minutes less. But we try to keep that minute. And the first presenter will be me, in water resource sustainability and the face of climate change, and followed by Dr. Alberto Tajida, sustainable IWRA, and also Dr. Efrem Yuskina also will have this presentation in water resource viability due to climate change, mainly from Mexico perspective. And maybe we can also make a question within each presentation, that after one presenter complete his presentation, we can also make questions. And but at the end of the 3 presentation, we have about an hour for discussion, based on the presenters. And we have also lunch break around 12:30, but they also informed that lunch will be ready at 1. And so I think here in the next quiz comment, we have so in the afternoon, we have also another session 2 on impact of climate change and water access, social, economic, and cultural aspects. And this will be chaired by Marinali Dominguez. And for each session, we have also chairman, chairperson, and also rapporteur. There's some of the basic issues in each presentation. I didn't mention the first session on integrated water resource management will be chaired by Dr. Judith Ramos. Maybe she's not already here. And the rapporteur will be Dr. Armando Sanchez. Maybe I should substitute with one of us here until they're here. And yeah, the afternoon session will be the climate change sustainable water access by Armando, and followed by environmental laws, policies, and adaptation measures on climate change. Will have to be made by Dr. Ryan Stoa from Florida International University. And the third topic will be social economic impact of climate change, will be by Diana. Diana, she came from Ecuador, from Ecuador. And the last will be sustainable management of lakes and extreme events, will be by Dr. Alfonso. I hope we'll see them soon because they told us. So for all that, we have also again a discussion about an hour. And after tea break, we have the session 3, that's the most important session, assessing sustainability of IWRA. And that will be chaired by Alfonso, and Diana will be the rapporteur for that group. And the first presentation will be in that session, water resource management in Mexico. That's by Cecilia. And followed by assessing IWRA sustainability by Aldo, we'll have him soon. And climate change, ecosystem and society by Dr. Judith Ramos. And we will have also discussion from 5:20 up to 6 p.m. That's discussion about the different presentation. Welcome. And after the discussion, we have also just like reception. That will be from 6 p.m. up to 8 p.m. So we have reception in another room, and I invite all of you to join that. That would be a chance to more interact and to have more discussion and informal discussion. And the next day, the second day on Thursday, April 25, we have one presentation in the morning from 9 to 9:20 by Dr. Claudia. That will be on climate change in Mexico. After having that presentation, we'll be divided into two groups. That we have two discussions on climate change in IWRA and assessing sustainability of IWRA. These two groups. So maybe we'll divide this group into two, so that we divide maybe today evening, the afternoon we'll indicate the two groups. So tomorrow morning will be divided into two based on our expertise, because we need to have more strong discussion about each topic. So on session 4 we'll have group presentations. That's the group chairperson will make a presentation about 15 minutes that will make a presentation of the outcome of each group. That will take about an hour. And we have also again discussion based on the two presentations. And in the afternoon, after lunch, we have general discussion and also a possible future research and development interventions. And we try to find how we as experts in water and climate change, and also from different institutions, from Florida International University, UNA, and other universities involved in the workshop, we try to find ourselves how in the future we try to develop issues already mentioned or discussed during the 2 days of workshop. That will be in the afternoon of the second day. And we have closing session. That will be Dr. Armando Sanchez will make conclusion and recommendation of the 2 days of workshop. Will give us a very summary of the 2 days achievement. And finally, Dr. Maria Reynoso will make the final remark or closing remark, and I will resume at 5 p.m. So depending upon our progress, in fact, we are flexible to shift time and move any presentation from here and there. So if you have any comment, any ideas, you are welcome. And now, according to our program, we invite Dr. Fernando Gonzalez.
Thank you. Thank you very much for inviting me to this session and to give this keynote speech to start with our meetings for sustainability of integrated water resources management in the face of climatic variability and change. I think it is a very important thing that you added climatic variability and change, because what I'm going to be talking today is what is the problems and challenges in a tropical environment in Mexico, basically, because of the climatic variability that is very high in our country, probably the highest that you can encounter around the world. And in addition to that climatic variability that we have, is some of the environmental impacts or perturbations of our watersheds because of recent development, especially in the tropical areas. We were asked by the national government of Mexico after the flood in 2007 So I'm going to be talking about sustainability of water resources in tropical regions in the face of climatic change. And basically what I'm going to be doing is describing what is the work that we did for is a very important part of the south and tropical regions in Mexico. And that began with the big flood of 2007. The big flood occurred in two of the biggest rivers in Mexico, the Grijalva and the Usumacinta. And we were asked at the university to make a plan, a basic plan, short-term at the beginning, and then a long-term plan to avoid the damages or to mitigate the risk of flooding in this very important part of the country. And so I'm going to be using some of these slides to show you what is the problems in the region and how the climatic change on top of all these problems is going to be a factor that we need to study and we need to face in the future of our tropical areas development. That doesn't mean that we don't have a problem in the arid environments. We did another study in the arid environments that were not presented today. But I think it is very important to quantify what the impacts are going to be, what the possible impacts are going to be. And after the quantification of that, what are the policies that we need to follow in order to adapt to what is going to happen in the future of climatic change. So this is a picture of what happens in our tropical forest. So this used to be 50 years ago, rainforest area, all covered by that. Well, 90% of the area was covered by rainforest. But basically this type of development, next one please, another picture of the same type of environment. You see some of the trees, just a little bit of what the trees were there, but basically we completely changed in the last 50 years the land use and the line and the soil cover of all the watershed. Next one. So that's another picture of how the forest was transformed in livestock land, rangeland. And the oil, again, the oil industry, Pemex, the refineries and the different things. And you see here a flat area. I'll show you what happens there. But this is a refinery and in the area, tropical environment also. And okay. So in a way, we have the last 50 years is a very high impact, environmental impact, and perturbation of our watershed, deforestation of 80% of the watershed. So we have, we've associated with that land use, increase the sediments. We modify the rivers with large dams and levees so that the regime of the rivers in the floods and dry season was completely modified. And we have the oil extraction again and changes in the rivers because of the dikes and levees that were constructed that modified completely the wetlands and some of the inundated areas in the region. So on top of that, now we have bad news. So most of what happened in the last 20 years is going to be changing. So I would say the stochastic process that described the stream flow and the rainfall is now changing, and we have, this is the Global Water Partnership that I was part of the foundation of that Global Water Partnership on board. Water is the primary medium through which climatic change will impact people, ecosystems, and economies. And I think it is a very important factor in our tropical areas. In general, impacts of climatic change on freshwater resources are expected to be negative. And I would say that we found in this tropical area and these watersheds, basically most of the impacts will be negative in the environment and the economic and the energy sectors. Again, the same in Global Water Partnership references the link between increased temperatures and changes in rainfall has been modeled in detail, but the same is not true for the effect of river flows and the literature on the groundwaters. So what we did here is we have modeled what is going to happen with the stream flow of the rivers due to the increase temperature because increase in evapotranspiration, and how that is going to affect the flows in the rivers, and how is the power generation going to be affected by a decrease in precipitation along the watershed, and how is that going to affect our coastal areas because of the sea rise due to climatic change in the future. See what that means? So in a way, what we did is try to see the climatic change effects on the two river basins. You have there the region. It's about 5% of our country, 85,000 square kilometers, and it concentrates about 1/3 of our stream flow. So we identify climatic changes and quantify them, assessing the vulnerability of water users and population, and defining adaptation measures to face the effects of climatic change. That's what we did. I would say this research was on top of the general planning for flood mitigation in the same basins. Okay? So you have a description here. Let me up here. See, this is the basin, again, what you saw here. You have an upper part in this place, where we have the big dams. You see the reservoirs here, the lakes. Then you have, this is the upper watershed. This is another watershed that comes this way, and comes from Guatemala, and goes all of it to discharge in the Gulf. And then you have the plains here, mountain area, the big plains here. This land is being really constructed in geological terms by the sediments that are coming down from the rivers of this part. So you can see that if you deforestate these parts in the upper part of the watersheds, you want to affect the sediment loads and the sediment deposits in the lower part. And that is the long-term effect that is being affected by changing the regime of the river's flow, the river flows by the construction of the dams, deforestation that I was talking about before. So we did the plan of how to operate the dams, how to deal with the natural reservoirs or wetlands in the lower part to see that we mitigate the effects of the floods. Next one, please. So the dams that you saw there comes from the upper part of the watershed, the lower part of the watershed, so 4 different dams that completely modify the regime of the river. So the mean stream flow, annual stream flow is basically more or less the same as the storage capacity of the dams. So one of the things is how to modify, and how is the climatic change going to modify the performance of the dams to generate electricity, and how are they going to change the possibilities of the dams to mitigate the effects of floods downstream. You have here some of the average annual precipitation in the watershed. This area here that you have in dark color is the highest precipitation in Mexico, and one of the highest precipitation in the world. Is more than 4 meters a year, and it goes for 2 meters to something dry in this part here, which is about 1,500 millimeters a year. And you can see that you have different effects in the lower part of the watershed. This is a mountain range here that goes to the Gulf, and this is another little drier area in the watershed. So different environments in the same watershed. Different, the same vegetation, different things, different development in that. But you have here we did analysis, all statistical analysis of something like 60 years of records. And you can see here some of the trends in the temperature. So these are the days with maximum temperature greater than the 90% of the cases. And you see that there's a clear, and this is the 5-year moving average, and this is the yearly amount. This is the percentage of the days that you have more than 90%. and you see clearly a trend in the last 30 years, 40 years in the temperatures. This is something in the tropical areas is that the difference of temperature, mean temperatures in the months is only 2 grades centigrades. But the precipitation trends do not show the same thing. So we cannot see any statistical significance in saying that you have an increase in or decrease in the total annual precipitation in the different stations that we have in the watershed. You have here what is the maximum precipitation for return period of 100 years and 20 hours of duration. So again, you can see that you have a high area, more than 200 millimeters here, 140 around the upper part of the watershed, and around 200 again in the part in here. So that gives you a measure of how the high, I would say, the storms, the different storms, and the low probability precipitation occur in the basin. And here you have a representation in the way that we use in the hydrology. It's a Gumbel distribution paper, and you can see for the different stations around the basin that you have different maximum precipitation for the duration of 24 hours. We made an estimation of how that distribution functions will change in the future. And we found difficulties to see that you can change from one to another, and with the information that we have. Next one, please. Now we applied to the same area, to the watershed, what are the different scenarios? When we choose the scenario A1B, which is balanced across all the sources, that see how that would we have a model and how the different variables will be changing in the future. So we selected A1B from our scenarios in the future, and we have again what are the zoning within the watershed. So this is the high part, the medium part, and the low part of the watershed, and we computed then what would be the changes according to the model, the global models, what would be the changes in precipitation and temperatures, and try to do something on the sea rise. And you finally got here for the high and medium and low, which will distinguish between the medium and low. For this scenario, what are the different increases in temperature? It's 0.9 for 230, and its increase is more, a little more than for the medium and the low part. This is for 2050. For the anomaly of the rain, again, for high, medium, and low part of the watershed. And then we did a combination of that for all the scenarios that we computed in the watershed. Now, with these formulations, what we did is, again, run a model modifying the precipitation records according to these numbers, and modify the evapotranspiration from the land and from the soil and from the reservoirs in such a way that we can then have a scenario of what happened with the stream flow and the storages in the dams under these kind of considerations. Sea level rise was a difficult one. We thought it was going to be easier, and we then tried to get all the different sea rises forecast for the Gulf of Mexico, that we thought, at least in the US, would be clear how much was that. But finally, we got to some conclusions here. We used 3 different sea levels increases. The most probably is going to be something like 60 centimeters, 2 feet. But we did it, the analysis for different ones. three different scenarios. One for, I think it's 1 meter, and then 1.5 meters increase in sea level. Next one, please. And then we run again the models that we have for the rivers, looking at the boundary condition of the ocean, increasing the level there, and we got, these are the levees that we used to have, and now with the increase in the sea level, these are the ones that we have to be constructed, so that we get what is the increase that we needed to cope with the increase in sea level. Next one, please. Now, the sea level, then we got a scenario for the 60 centimeters. And now for the rest, the annual average temperature is projected to increase 1.6, and the annual rainfall decrease in 5% in the upper part of the middle basin, and there is no variation. The lower basin is projected to decrease by 2.5%, so that we got from the global models adapted to the region. Runoff volume decreases gets its maximum in Chicoacén. Chicoacén is the middle dam for power generation. So the runoff decreased 60% in the average. The higher decrease in hydropower generation observed in Malpaso, 25%. Malpaso is the lower dam. So the hydropower generation in the Guajira system is estimated in 3.6 billion pesos per year in loss of generation, power generation. Yes.
Excuse me, and that's for the whole system or just?
For the whole system.
For the whole system.
This is just a summary. So we made hundreds of different simulations in the system to see how much was affected in the upper part, how much in the lower part. Now, I think we made a list of what the studies and all the action are needed. And one is reduce the uncertainty for climatic change models as well as on extreme events. So it is very difficult for a watershed that is having so much problems to talk to the people, and especially politicians, and say, well, you see, we probably will have these scenarios in the next 50 years. So you have to invest now to see that you want to cope with this long-term future scenario. With the type of uncertainty that we have in the world, and you're trying to really quantify how much power you're going to lose, then you see that the reliability of the models is not enough for that. So how do we get less uncertainty from the models? I think that's a challenge. Update the hydropower projects portfolio. So we know that it's going to be reduced, the 20%, so we need to find some other ways to generate the power that's going to be lost. Implement natural resource conservation projects. On top of all the perturbations that I told you, I think that the climatic change will put much more pressure on that. Prevent impacts on other sectors, for example, the health. I think that if we have uncertainty in forecasting what is the effect of climatic change in power generation, the uncertainty that we have in looking at what are the impacts on health for future is much greater. And intensify dissemination of studies and research results on climatic change. Next one, please. Well, probably the most important issue here is that the results that we have for the extreme precipitation events do not show an increase in intensity according to the models, according to the records that we have, but that contradicts in some way what is said in the literature. But probably that contradiction comes from the fact that there is some influence of the hurricanes, tropical hurricanes here. And we have very little research and very little results on how climatic change could affect the intensity of hurricanes. And I think it's a lot of talk on that and very little, I would say, serious work that could determine the ways that the climate change could affect intensity, precipitation intensity in hurricanes. These are the principal findings that we have. And as I tell you, just telling you one section of our research, which was in fact dedicated to mitigate the effects of climatic variability on the basically the plains, Tabasco plains, in the watersheds of the Galvano Okay, I'm ready to answer or hear the comments.
Thank you for Dr. Fornaro for an excellent presentation. And we now can also open for discussion if you have some questions.
Yeah, well, I think I have a comment. In terms of the model that was used for, let's say, to produce the scenarios, it is a moderate sort of the emission scenario, the 1B that you present, or these balanced sources. It's a moderate one, and therefore you have relatively small changes in precipitation of the order of 6% or 5%. There are two issues here. Maybe it's too moderate for planning. The point that I want to do is that somehow we have to deal with uncertainty. You see, of the uncertainty that these studies are immersed in. This does not show the whole story, because it's one of the moderate emission scenarios. And the other question is, if that 6%, if you could translate that to money, that's a lot of money. So that means that even a sort of moderate scenario for the future with a decrease in 6%, it's a lot of money. Means a lot of money. So if the thing would be worse, it would be much more expensive. So again, we have to start acting in terms of these large uncertainties.
Yeah, I fully agree.
Well, I think it's an admirable piece of work. Right now, you've gone this far analyzing the colors. Have you done, or have done some analysis which are of the same depth of some other interesting basins, and have there been an inter-basin comparison just to know if things what I've shown is the same or not?
Yes, we analyzed the Sonora River watershed, which is close to Arizona, is the arid environment of Mexico. And we found there that the impact of decrease in precipitation amplifies much more on stream flow that we found in this area. So for the area of Sonora Basin, we found something like 35 to 40% decrease in stream flow. And that would mean that you will have big impacts on the water supply for Hermosillo, the capital of Sonora, which is 1 million people, more or less. And you will find an increase in conflicts in the basin to use the more scarce water in the future. So increase demand, decrease precipitation, an amplification for decrease of 30 to 40% in stream flow, you will get a high pressure on the water resources. So I think it's a different impact in the north, in the arid environment, than it is in the tropical environment. I don't know which could be worse, but I think it's something that we need to start acting or thinking, at least thinking today, and be sure that you take long-term plans and give the big point of this is how do you translate that into action and investment? I think that's important, the biggest part of it.
I have a question. I saw that you use something like an assumption of a Bunge distribution. I think that is because of the stream values, the way to handle these stream value things. So have you tried to model these impacts using different distributions? I mean, with heavy tails, for example, wide bulls, or try a different statistical assumption on the distribution of the data?
We have done quite a lot of work on the statistical distribution of stream flow and precipitation. And but I think that Combo distribution, which is Combo is an extreme distribution for extreme values, independent of the distribution of the annual values, fit better basically most of the rivers in Mexico. And in some of the parts of Mexico, especially the north, we have work some years for here in the university. We call it the double Humboldt distribution because you have two different populations. One is if you have hurricanes, then you have basically low precipitation. You have hurricanes, then you have another population. This double Humboldt probably fits better. In this case, we tried a different distribution and we still found that the Combo distribution is better than the data that we have.
No, I just wanted to see if you have done any comparative studies in terms of the incidence of the potential influence of climate change vis-a-vis other drivers, for example, extreme, even more than what is now, deforestations or population growth, land use changes, and what is, if those studies have been done, how do you position climate change vis-a-vis these other drivers that are in that part of Mexico also extremely critical?
Very good question. We tried to do that to simulate, say, the same watershed with all the vegetation that we had 50 years ago, and then make a simulation of the stream flow with the same record of precipitation. And then without, with deforestation, that what is now the regime that we have in the rivers, we haven't done. We're trying to do that. We're not getting the funding for it, so that's been delayed. But I think it would be very, very important to see what is the size of one perturbation against the other one that comes in the climatic change. I think that that's something that bothers us. But it is not easy. It is easy to say that changes, of course, that changes a lot. But then any model that you have, the calibration of that, it gets very difficult in practice. We can do it. And I think it's a good idea that we can list that to try to see at the end of the seminar if we could really be interested in doing, comparing the last 50 years, the impact that we have in the watershed, compared with what we would expect in the next 50 years because of climatic change. Probably it's that. I think it's a good idea. We haven't done it.
Thank you very much. It was a very interesting discussion. And before I